Let's look at the question. Optimize water distribution in a village. There are n houses in a village, and we want to supply water for all of the houses by building wells and laying pipes. And for each house I, we can either build a well inside it directly with the cross wells at I-1. We use I-1 because it is zero indexing, or piping water from another well to it. So the costs to lay pipes between houses are given by the array pipes, where each pipes at J is a 1D element array which contains 3 elements, house 1J, house 2J, and cost of J, which represent the cost to connect house 1J and house 2J together by using a pipe. So the connections are biconditional, and there could be multiple valid connections between the same 2 houses with different costs. And finally, we should return the minimal cost to supply water to all of the houses. In the first example scenario, they have 3 houses, and the cost to build a well in the first house is 1, in the second house is 2, and in the third house is also 2. And they have 2 pipes, one connecting the first one and the second house with the cost of 1, and the other connecting the second and the third house with the cost of also 1. The cost of connecting houses using pipes is 2. So the best strategy is to build a well in the first house with cost 1 and connecting the other houses to it with the cost 2. So the total cost is 3. In the second example, we represent a scenario where there are 2 houses. The cost to build a well in both houses is also 1, and there are 2 pipes, one connecting the first and the second house with a cost of 1, and the other connecting the first and the second house with a cost of 2. But we will always choose the cheapest option. We can supply water with cost 2 by using one of these 3 options. The first option, we build a well inside house 1, which costs 1, and we build a well inside house 2, which costs 1, so the total cost will be 2. The second option, we build a well inside house 1, which costs 1, and connecting house 2 with house 1, which costs 1, so the total cost will be 2. And the third option, we build a well inside house 2 with cost 1 and connect house 1 with house 2 with cost 1, so the total cost will also be 2. In the third example, if we build a well in each house, it would be a more expensive solution with a total cost of 15. And if we connect in the houses without building any wells, it would be also a more expensive solution with a total cost of 14. The optimal solution would be that we build a well in the 5th house with a cost of 1, and if we build the pipe between the house 4 and house 5, it will cost 4. It is very expensive, we should avoid that. So we try to build a well in the first house with a cost of only 2, and then we connect the remaining house 2, 3, and 4 to the first house with the pipes, so the total cost will be 12, and the answer to the output of the third example is 12. Since the problem description involves connecting houses using pipes, we can tell that this problem is a variant of graph problem. Houses are the vertices and the pipes are the edges, and more precisely, we can convert it into a standard minimal spanning tree problem. Concerning the minimal spanning tree problem, there exist several classical algorithms. In particular, we will demonstrate 2 of them, namely Prim's algorithm and Krask's algorithm, which are arguably the most popular ones and feasible to implement during an interview. First of all, let's introduce the problem of minimal spanning tree. Given a connected, edge-weighted, and undirected graph, a minimum spanning tree is a subset of edges that connects all vertices, while the total weights of these edges are minimal among all possible subsets. One can draw some similarities between the above definition and our problem here. Specifically, we can consider each house as a vertex in a graph and the pipes between the houses as edges in the graph. However, there is a major difference between them. In our problem, every vertex and every edge comes with a cost, while in the setting of the minimal spanning tree, only the edges are associated with the cost. So, to bridge the gap, the trick is to add one virtual vertex to the existing graph. Along with the addition of the vertex, we also add the edges between the virtual vertex and the rest of the vertices. And finally, we just reassign the cost of each vertex to the corresponding newly added edge. Let's try to illustrate how we convert the graph in the example with the above tricks. So With the converted graph, we then can take into account the cost from the vertex via the additional edges. We can focus entirely on selecting the appropriate edges to create a minimum spanning tree. Thus, our problem is simplified to creating a minimum spanning tree from a tree of weighted edges. So in the above graph, we demonstrate the solution that we will find after we solving the minimal spanning tree problem, which we can translate the problem as: to minimize the cost, we should dig a well in the house indexed with 1, denoted by the edge between the indices 1 and 0, and then we just apply the water to the rest of the houses.